Welcome to another edition of Math for No Reason. In this edition, we deal with a problem of probability. So we have a random variable x whose moment generating function exists. What does that mean? It means that the expected value of e to the power tx is finite for all t in a neighborhood of 0. So for all t belonging to minus u to u for some u. Then we have to prove that probability of x greater than equal to a is less than equal to expected value of e to the power lambda x divided by e to the power lambda a. Now, the expected value of e to the power lambda x has to be finite for the chosen lambda, and this is the MGF of x. To deal with this result, we will invoke the Markov inequality, which says that if x is positive random variable, then probability of x greater than equal to a is less than equal to expected value of x divided by a for all a greater than 0. Now, we look at probability of x greater than equal to a as given here. Note that for the given random variable, there is no restriction that x has to be positive. So we are looking at probability of x greater than equal to a, and suppose lambda is positive. So if we multiply both sides of this with lambda, so we get probability of x greater than equal to a is equal to probability of lambda x greater than equal to lambda a, and we know that e power x is an increasing function. So this is equal to probability of e to the power lambda x greater than equal to e to the power lambda a, and by Markov inequality we know that this quantity is less than equal to expected value of e to the power lambda x divided by e to the power lambda a, provided the MGF exists. So this inequality is well known and is known as the Charnoff bound. So this bound on the right hand side is known as the Charnoff bound. So now we will use this result to derive an inequality about the normal distribution. Now for the normal distribution, we know that the MGF of standard normal is e to the power lambda square by 2 if I consider the variable to be lambda. Instead of t, if we write lambda, the MGF of a standard normal distribution is e to the power lambda square by 2. So, probability of x greater than equal to a is less than equal to expected value of e to the power lambda x divided by e to the power lambda a. And note that the MGF for the normal distribution is finite for all lambda. So this is e to the power lambda square by 2 minus lambda. So the probability of x greater than equal to a is less than equal to e to the power lambda square by 2 minus lambda a, and this is true for all positive lambda. Now what could be the lowest bound for this? So let us try to study that. So we want to study the function f lambda, which is e to the power lambda square by 2 minus lambda a as a function of lambda for lambda greater than 0. Now the derivative of this function is e to the power lambda square by 2 minus lambda a into 2 lambda by 2 minus a, and we see that this is e to the power lambda square by 2 minus lambda a into lambda minus. So the derivative is 0 implies, so this is a critical point. So lambda equal to a is a critical point, and what kind of a critical point it is? So if you think of the point a here, so to the right of this it is increasing. If lambda is to the left of a, then the derivative is negative and the function is decreasing. So in the neighborhood of a, the function is first decreasing and then increasing. So lambda equal to a is a point of local. In this case, local is actually global, since there is only one minima, and so therefore the local minima also becomes the global minima. And what is the value when lambda equal to a? So f of a is e to the power a square by 2 minus a square e to the power minus a square by 2. So f of a is e to the power minus a square by 2. So the least value on the RHS is e to the power minus a square by 2. But note that we are arriving this when lambda equal to a and lambda is positive. So we are actually showing that this is for a greater than 0. Thus, we have shown that probability of x greater than equal to a is less than equal to e to the power minus a square by 2 for a greater than 0. That's a good point to stop. Thank you.